So, we are looking at flow through ducts and various different drivers which affect the compressible flow through ducts. One change that was we started with was the variation of area, which is variable area ducts. Then we looked at friction, effect of friction separately, constant area duct with friction, which was Fano flow. And now we come to the case where we are taking a constant area duct and there is a heat transfer across the duct. So, the duct is no longer adiabatic. In the previous cases there was no heat transfer. Now we take pure heat transfer, which is this kind of flow is known as Rayleigh flow. We are taking them separately so that we can understand in essence what happens when the dominant effect is due to either one of them. And then later on towards the end of this section, I will give a quick introduction to how one can look at combinations of parameters in what is known as a generalized quasi 1D analytical procedure or equations. But that would be just an introduction. When we are considering these flows, they are taken separately, and the essence of these or the understanding obtained from these flows are very important, and they do not change by a great deal when we are looking at more complex flows. So, what are we looking at in this case? This is the Rayleigh flow, and in Rayleigh flow we are looking at heat transfer or heat addition to the flow as the flow occurs in a constant area duct. Now, the heat addition or it can be even heat removal, it is a non adiabatic process. So, that means heat can be transferred. That can happen, both heat addition or heat removal can happen. It can be due to heat transfer, or heat addition can also take place due to heat released from chemical reactions such as combustion. This can also be modeled in terms of a Rayleigh flow. And let us take Q as the amount of heat supplied per unit mass. So, the flow is not adiabatic. So, this is wrong, the flow is diabatic, that is it allows heat transfer to happen. So, the governing equations they are the mass flow rate through the system remains constant. So, rho 1 V 1 is equal to rho 2 V 2, area is same. Then P 1 plus rho 1 V 1 square is equal to P 2 plus rho 2 V 2 square. Here we are considering frictionless flow. So, the frictional factors are not coming in picture, that means momentum is conserved. Okay. What about the total enthalpy? H 1 plus V 1 square by 2 plus there is a heat added term. So, there is addition of heat. Q is actually Q dot which is total heat added divided by m dot. So, per unit mass. So, Q is equal to H 2 plus V 2 square by 2. Okay. So, there is a heat added term. Okay. In calorically perfect gas, H is Cp multiplied by T, okay, Cpt. Okay. So, Q is essentially Q is H naught 2 minus H naught 1, which is Cp T naught 2 minus T naught 1. Okay. So, this one should understand. So, if there is heat addition, then heat added, that is Q is greater than 0, that is your stagnation temperature will rise, T naught 2 is greater than T naught 1. If heat is removed from the system, then Q is less than 0, that is stagnation temperatures will drop. So, this is in essence what we are looking at, and similar to the Fano flow, we will first start by looking at the thermodynamics of the process. We will put some charts, very easy to understand them with charts, and that way we will understand almost everything about the flow with heat addition. So, here also rho b is constant. So, that is rho b is g. Again this parameter g comes here. Momentum equation, p plus rho v square is equal to constant, that is p plus g v is constant. Okay. So, that is p 2 minus p 1 is equal to g multiplied by v 2 minus v 1. But what about v? V is actually g by rho. Okay. So, if you can use g by rho, which is g multiplied by specific volume. Okay. So, the momentum equation can also be written in terms of g and specific volume. P 1 plus g square v 1 is equal to p 2 plus g square v 2. Okay. Now, you can do p 2 minus p 1 is g square into v 1 minus v 2, which is negative of v 2 minus v 1, or p 2 minus p 1 by v 2 minus v 1 is equal to minus g square. Now, this is the equation of a straight line. Okay. So, the Rayleigh lines or Rayleigh curves, if written or if drawn on PV diagrams, P and specific volume V is they are actually straight lines. Okay. And from here you can understand this term p 2 minus p 1 by v 2 minus v 1 is equal to minus g square. G square has to be a term which is positive, that means p 2 minus p 1 by v 2 minus v 1 has negative slope. So, that is very important. So, they have always have negative slope. Okay. Then you can relate g with the slope of the PV Rayleigh line in the PV diagram. If tan alpha represents the slope of the PV diagram, then g is nothing but negative square root of negative tan alpha. Okay. So, we then the velocity can also be represented now along the line as the specific volume multiplied by g, which here is minus tan alpha. So, it is a very nice way to represent this particular line is known as the Rayleigh line. Okay. So, in the Rayleigh line is described by looking at the continuity equation and the momentum equation. Okay. And in PV diagram they are straight lines. Okay. And you can draw isotherms and isentropes, the curves of constant entropy and curves of constant temperature along these same PV plane, and that will tell us about how temperature changes and pressure changes in these curves. Okay. So, now they can also be plotted in HS diagram or TS diagram, similar to Fano curves. These curves also have two branches. There is an upper branch and there is a lower branch. The way the curves look as of this kind, it is different from a Fano curve, of course, but you can notice some important differences. One is that if you look at the upper branch, which corresponds to the subsonic flow, Mach number is less than 1. Okay. So, if you take this upper branch and you see how temperature varies in this branch, first the temperature increases up till a maximum of temperature. See, temperature maximum is achieved at this point, and then temperature decreases, okay, until another point is reached. This point corresponds to maximum entropy, okay, S max, maximum entropy S max. Okay. So, if you look at this curve, the upper branch, which is a subsonic branch, initially there is an increase in temperature. After reaching a point where T is equal to T max, maximum temperature, then its temperature decreases until it reaches S max, where maximum entropy is achieved. Now, if you look at lower branch, which is here, here the temperature continuously increases. Okay. So, very important point in Rayleigh curves is there are two critical points, one is maximum temperature, the other one is maximum entropy. Now, in order to understand this clearly, you should also look at the stagnation temperature lines, because it is or stagnation enthalpy lines. The stagnation enthalpy line will now have two branches similar to the stagnation, or rather similar to the Rayleigh curve. It will not be H naught is not constant like that, like it was for the case of Fano flow. So, here if you add heat, always the stagnation enthalpy increases or T naught increases. So, going from 1 to 2, increasing in this direction, there is an addition of heat. So, T naught increases. So, the lower branch of this curve corresponds to subsonic flow, because this height here, this difference should correspond to V square by 2, right, by the equation. So, this height should correspond to V square by 2, right. So, the lower one corresponds to Mach number less than 1, while the upper branch corresponds to Mach number greater than 1, and they reach a cusp, rather they reach a point at which maximum heat can be added, and that particular cusp corresponds to the point where entropy is maximum, S is equal to S max. Okay. Then Q is equal to Q max, maximum heat that can be added. So, this point should be is very important, and also notice that here you have a line. If you draw an isentropic line for a point 1, you have T naught corresponding to that, and T star corresponding to the point where it can be isentropically brought to Mach number equal to 1. Even this T star is varying, because now heat is getting added into the flow. So, T star and T naught are not constants. So, do not confuse between isentropic flow, Fano flow and Rayleigh flow. Rayleigh flow is not an adiabatic flow. Therefore, T star and T naught star or T naught, they are not constants. Now, we know how pressures are depicted along Hs diagram. So, if you look at the curve itself, you can make an understanding, or you can get an understanding of what happens. For subsonic flow, when heat is added, you see that this height increases, that means velocity increases, Mach number increases, pressure decreases, temperature increases until a particular point, maximum the maximum enthalpy point, and that particular point can be shown to be equal to 1 by square root of gamma. After this point, the temperature decreases. Why this is happening? Why should temperature increase at a point and then decrease? This is because actually what you see is that addition of heat affects total enthalpy, which is T naught or H naught. H naught is a combination of H plus V square by 2. This is static enthalpy, and V square by 2 is kinetic energy. Okay. So, for the initial region of this subsonic branch until the point of maximum enthalpy, the increase the addition of heat goes largely to increase static enthalpy and less to increasing kinetic energy. Of course, V is increasing, but it is to do with the relative increase of the two. initially the relative increase is more towards increase of static enthalpy, but once you reach maximum enthalpy point, further addition of heat actually increases kinetic energy enormously, and some amount of it actually can also be taken from the static enthalpy. So, total enthalpy, which is a combination H plus V square by 2, that continues to increase, but static enthalpy reduces, because now more amount of energy is taken by the kinetic energy. So, that is why this happens. So, you have to view this as a combination. Your H naught is increasing all the time when you add heat, but they are a combination of static enthalpy and kinetic energy. Okay. T naught or stagnation enthalpy increases, P naught actually decreases. Okay. P naught decreases, because you find here that even here not only just that entropy changes. So, you have to work out the equations here. So, that needs to be done. Okay. In case of supersonic flow, when you add heat, okay, the addition of heat causes Mach number decreases. So, velocity actually decreases, pressure increases, temperature increases, T naught of course definitely increases, P naught also decreases. Okay. So, this is evident from this Rayleigh curves. Now, how do we get to these limiting points? So, this is what was meant. So, if you look at the PV diagram, these straight lines, this particular straight line is the Rayleigh line. Okay. Now, if you look at the curves at which H is equal to constant, okay, this is static points of sort of constant entropy, S is equal to constant, okay, and points at which temperature is constant, that is enthalpy is constant. Okay. They are two different curves and we know they are related to each other. So, the entropy curve has a higher slope than the enthalpy curve. So, this is T equal to constant and this is S equal to constant. This difference is there as a consequence. So, where is this point of maximum temperature? It is a particular point where this Rayleigh line becomes tangent to the temperature equal to constant curve. Then whenever it becomes tangent to the entropy equal to constant curve, S equal to constant, then that corresponds to maximum entropy. Further beyond that you do not have any solution. Okay. So, you can see that these are two different points here. So, how do we get that? The slope. So, because we look at the tangency condition, tan alpha, that is the slope of the Rayleigh line, is g minus g square, that is we have established that is minus v square by nu I mean v square, that is specific volume square. This can be expressed in terms of Mach number. If you do multiply and divide by gamma p, then this is a square. So, you get minus gamma p by v minus gamma p by v m square. Okay. Now, what about the slope of isotherms? That is taken as tan delta, which is dou p by dou v at constant temperature, and we know the ideal gas equation of state, and from there we can find out when temperature is constant what is the slope of the isotherms or isotherms RT by V square. Then RT by V is minus P by V. So, now you can at the point of maximum enthalpy, that is a tangency condition between maximum or temperature constant curves and the Rayleigh line. So, gamma p by v m square is equal to p by v. So, from here you get m square is equal to 1 by gamma or m is equal to 1 by root gamma. So, this establishes the relation for the point of maximum temperature. Now, what about the limiting point of maximum entropy? We should look at the tangency condition for the Rayleigh line tan alpha with the entropy line isentropes. Okay. So, S equal to constant lines. So, if you look at that, take tan phi is dou p by dou b at constant entropy. This is minus v square dou p by dou rho at constant entropy. Dou p by dou rho at constant entropy is speed of sound a square by v square. So, tan alpha equal to tan phi. So, v square by v square, that is specific volume square, is equal to a square by v square, or p square equal to a square, or Mach number equal to 1. Again we find that at the point of maximum entropy Mach number equal to 1. So, and that also represents a switchover point between subsonic flow and supersonic flow. So, in all the different cases variable area ducts or Fano flow or Rayleigh flow, Mach number equal to 1 was a critical point. In all these cases it is a critical point, but they are different descriptions. So, they are not the same point. In a Fano curve it has to follow a Fano curve to get to point Mach number equal to 1, and then it is a critical point in the Fano curve. In a Rayleigh curve it has to follow a Rayleigh curve or a Rayleigh line, and it has to reach Mach number equal to 1, which is a critical point. This point also corresponds to the maximum Qmax, that is maximum heat added kind of situation here. Okay. So, if you add heat in a subsonic flow, it drives the flow towards Mach number equal to 1. Similarly, if you add heat to a supersonic flow, it also drives the flow towards Mach number equal to 1, and the maximum heat that can be added corresponds to the point where maximum entropy line lies, and that also is equal to 1. So, the point why you get Mach number equal to 1, Qmax is also on the same line, is slightly different from the point where if you consider an adiabatic flow like the frictional flow, Fano flow with friction, you cannot have the flow going smoothly from a subsonic flow to supersonic flow. In case of a Fano flow, it will, this is a Fano flow and you have S max and Mach number equal to 1, subsonic branch, this is supersonic branch, and one cannot go from one branch to the other branch because this is an adiabatic flow, and here entropy has to be always, delta has to be always greater than 0. So, this is the condition here, but this is not an adiabatic flow, but here only by means of heat addition one cannot go beyond Mach number equal to 1, because if you look at the stagnation curve, that corresponds to maximum heat added. Okay. So, you cannot add heat beyond Qmax, maximum heat, there are no solutions beyond that. So, you cannot move beyond subsonic to supersonic just by means of heat addition, or supersonic to subsonic just by means of heat addition. The reason is somewhat it is a fine point, it is somewhat different from the point why it is the same for the Fano flow. Okay. So, now when we look at Rayleigh flows similar to Fano flow, now this has been a qualitative understanding, but more or less all the different conditions of Rayleigh flow can be understood by means of a Rayleigh curve similar to Fano curve. If you understand this curve thoroughly, then you understand almost all aspects of Rayleigh flow. So, please learn to draw these curves qualitatively. and distinguish the various points. Okay. So now we what we want to do is solve situations where we come across Rayleigh flow. There the points would be that you would know how much amount of heat is added, and you know points in region 1, you would want to know what happens to region 2. Okay, so this is a typical problem. Then how would we go about this particular problem? So the guiding principle here is that Cp T02 minus T01 is equal to Q. So this is the guiding principle. Then we seek, all similar to the other cases, we seek the ratios P2 by P1, T2 by T1, rho 2 by rho 1. They should be expressed solely as functions of m1, m2 and gamma. For a calorically perfect gas, gamma is a constant. Okay, so T02 by T01. So that is what we wish to do, and T02 can be determined by using this particular equation. So once you know T02, T02 by T01 can be determined. If M1 is known, M2 can be known, and this can be done. But we would look at the equation soon. We will find that again solving them is quite tedious task. So we always use a reference point for the Rayleigh curve. The reference point is going to be the maximum entropy point, where Mach number will also become equal to 1. So for a given Rayleigh curve, this point is fixed. It is a fixed point for that particular Rayleigh curve. Okay, so that is a reference point. You have it in terms of star values. So P by P star, T by T star, and rho by rho star. So now again clearly distinguish between all the different processes. The star value that you got in a variable area duct is due to an isentropic process. It is different from the star value you get when Mach number 1 is achieved in a Fano flow. It is due to a process of having friction in a constant area duct. Similarly, you can drive the flow to Mach number equal to 1 in the case when there is heat being added to the flow, and in that case you get the Rayleigh flow, and you get a Mach number equal to 1 in the case of Rayleigh flow also. These three conditions are not the same, so don't ever take them to be the same. When you are considering Rayleigh flow and Rayleigh curve, the star condition is corresponding to Rayleigh curve. When you are considering Fano flow, it is corresponding to Fano flow. So this part you have to take care. So the equations, how to solve them, we will discuss in the next class, and thank you.